Last lecture we started with the DC machine and we explained two important equations. The equations for the induced EMF, called armature voltage, and its proportion to the flux, phi, and to the speed, and constant of the machine, which depends on the dimension of the machine. The second important equation, the torque development, the torque in the DC machine, and it depends also on the flux, but not on the speed as in the voltage. It depends instead on the current, armature current, and also the size of the machine, the dimensions, which is expressed in the constant Ka. And we solved one problem, one example last lecture, how to calculate the voltage, the induced voltage, how to calculate the torque. Today we'll continue, and we are going to start with the DC generator. It will take maybe 2 lectures, and then we'll start with the DC motor. For the DC generator, it's a DC machine, and how can we find the equivalent circuit? If you look at the machine, the DC machine, you'll find you have, let's say, 2 poles, just to make it simple. And you have the armature. And the north and the south pole, you might have electromagnets. So maybe you have a coil here. And you connect it to the supply. So let's say that the voltage applied to the field to create the magnetic field, to create the electromagnet. And this circle, that will be the cylinder, the armature, where we are going to put the winding. And the, if you say that the axis here in the middle, the neutral axis, then if you put like wire here, that will be the other end. So it's going in and coming out around. So if, let me sketch, if you have the rotor in 3 dimensions like that, and you have space slot here that you put the wire, and then on the other side there is one, but we cannot see it. So if you put one winding here, one wire, you go here in the back, and then you're in the other slot, and then you bring the other end. So that's one term. And then you can, so if you, let's say that the current go in this direction, you make a dot here. So when you read the notes that I already posted in the folio, so you understand what means the plus and the dot. The plus, it means that the current in, and then the dot, the other side of the term coming out will be the dot. And you can distribute, of course, many conductors. So you have here the positive side, and that's the dot, the current coming out. All right. So how you represent the turns of the winding of the armature? You can represent as also a coil. All right. But there are 2 important facts about the armature. First of all, if you have the brushes, let's say that you have the brushes here. You have the brushes here, and you want to have to this machine to operate as a generator. So you are going to get the voltage output where you are going to connect the load. So that will call the voltage terminal. So the machine will produce voltage. But this voltage across the terminals of the DC generator will be less than the induced voltage or the voltage generated across the armature winding between the brushes. You can say that the voltage here produced inside the machine, as we call it, EA, the induced EA. That's the pure voltage produced by the machine, armature voltage EA. So to go to the terminals, so some loss in the resistance of the winding, which you can represent it as a resistance. We call it RA, the armature resistance, and the current going out there, the current going to the load IL, where you are going to connect the load to the output terminal. That's the voltage VL. Sometimes you call it VL, VT. So it's the terminal voltage or the load voltage, both are the same. So this voltage will be less than EA, the induced EMF voltage by the drop across the resistance RA. So how can you sketch the equivalent circuit of this generator or this machine? And by the way, the same equivalent circuit for the DC generator is the same as the only difference, the direction of the current. So let's just start with the DC generator. So first of all, this the terminal side, it can be represented as that's the armature, and that's the brushes. And we'll say that you have positive, negative, and EA is produced between the two brushes. And then you can represent the resistance of the wire, of the winding of the armature by resistance, and you can call it RA. So that's the RA, armature resistance. And that's the other terminal. So the voltage across the terminal, V, and sometimes we call it VL, the load voltage. If you the load, let's say that if you want to connect load here, so have the load, if you wish, that's RL. And the current will be coming out of the generator of the armature going to the direction of the load. You can call this IL, which is the same I load. And the current in the armature going here, it's IA. In this case, IL is equal to IA. As you see, there is no division in the current. What about the field, the north, the south, the flux, how you represent the circuit? It's very simple, because as you see, we just make a coil around N and S, and then you got voltage, if the current going this direction. So it's just like a coil. So you can represent it as and it has resistance. Most of the time, we need to adjust the field current. So we add an external resistance, we call it the field control resistance. And that's connected in series. And here you go, the voltage. You can call it VF. And if you say that's positive, that's negative. And the current going from the source to the field, that's IF. So the resistance of the wind of the field wind called RFW. The resistance of the field wind. And this resistance, that's usually it's the stat, variable resistance. And you call it R field control. That you change it. Why you would change it? So you can control the current in the field. Why you want to control the current in the field? Because when you control the current in the field, you control the flux. Phi. Why you want to control the flux? Because you can control the magnitude of the voltage. Simple. So when you are connecting the field to an external source, we call this DC separately generator. So that's separately. That's first of all DC generator, the equivalent circuit. And what's the type? Excited. DC generator. Why we call it separately excited? Because the field is connected. The source for the field is separated from the output voltage or the terminal voltage. They are not connected. The equations of this generator, very simple. First of all, we can, if we look to the right-hand side, you got the field circuit, and it's very simple circuit. You have only voltage source called VF, and you have only two resistors connected in series. You can, if you can combine them in one resistor, you can say the resistance of the field is equal to the resistance of the field winding plus the resistance of the field control. So when you add them, you get the total resistance. Once you get the total resistance, you want to calculate the field current. It's very simple. It will be like Ohm's law. We have IF. The field current will be equal to the voltage of the field divided by the total resistance of the field. We are done with the field circuit. Now we'll go for the armature circuit. That's the other half to the left. So when you look for the circuit, what you have voltage VT or VL, whatever, and you have another voltage EA and resistance, only one resistance, armature resistance. So how you can you write the VT? Of course, the terminal voltage across the generator will be less than the induced EMF or the voltage across the armature EA because of the drop voltage across the resistance RA. So it will be equal to the EA minus RA IA. That will be the drop voltage across the resistor. So that's the terminal voltage. We have question number one: how the induced EMF or the armature voltage is produced, from where? It's a generator. So if you sketch the generator, just simply is like that, and you have shaft. This shaft is connected to a prime mover, and the prime mover, it will rotate the shaft by speed omega m. What's omega m? It's the mechanical speed, radian per second, and there is torque on the shaft. We call it TS. So this torque produced by the prime mover. The prime mover can be anything: internal combustion engine or turbine connected to. So it's just like, I mean, anything that you move the shaft. In external force, move the shaft of the generator. That's the DC generator. So what happened? That voltage is produced. So EA will be, if you like to put it in the diagram here, that you say that there is a shaft here connected to the prime mover, and this one is rotating by omega, and the torque of the external force or external energy source, that's TS, the shaft torque. So TS, let's call TS, that's the torque of the shaft torque, and that's also a Newton meter. And omega m, it's the speed, the angular speed or mechanical speed of the shaft, and that's radian per second. And if it's not given, only n revolution per minute, so you can say that omega m, we can get it by pi, as I said last time, times n over 30, and this n is the speed revolution per minute. So we have the input. The input is mechanical. That's obvious for the generator. You have to have external mechanical hit the engine. So that's what is going to produce EA, and that's why when we wrote the equation last time, said EA is equal KA, the constant that we explained last time, multiplied by the phi. Phi is the flux per pole, and the speed omega m. That's how the voltage produced EA. Of course, here the torque is not produced. The torque is applied. It's external torque. So now I have the only equation to calculate the voltage produced, and I can continue to anything that we need. Well, let's see. Take one example for how to do this calculation. Numerical example. Let's say that we have a DC machine operating as a generator, and let's say that the resistance of the armature is equal by 0.1 ohm, and the voltage at the terminal that was equal to 200 voltage, and the resistance of the field is equal to 200 ohm, and usually the resistance of the field is much higher than the resistance of the armature. So, and let's say that the load that needs current needed by the load is equal to say 20 amp. So when you look at that, you got to have the equivalent circuit. So you just make it like that. That's the armature, and then you make the resistance in series. You can collect the all resistance RF, and we know it consists of two parts. Say that the field is equal to 250 voltage. So that's the voltage, 250, that's the VF, and the resistance is equal to 200 ohm. Sure, resistance is equal 0.1, and the current is equal to 20 amp, and that's the voltage on the terminal, 250. Of course, there was a load there that to take this current. Pardon me? That's 200, yeah, it's 200. So the question is, just let's calculate the value for the EA. It's very simple. We say that the terminal voltage here, that's equal to the armature minus RA IA. And so the induced EMF or armature voltage is equal VT plus the drop RA IA. And the terminal voltage is equal to 200. And the resistance is equal to 0.1. And current in the armature is equal to 20 amp. So that will be equal to 200 plus 2. So it will be 202 voltage. So the voltage produced in this machine, 202 across the armature. Type of connections, yes, we do. In this one separately, because the field is separated from the armature, but you can connect, if you have the machine like that, and you connect the field across the armature. So what's happening now, you do not need extra source for the field. The field is already has the same voltage across the armature. We call this shunt DC generator. Shunt DC machine, because the same connection that we are explaining now in the generator, the same is applied for the motor. So that's shunt DC motor, and you don't need two sources, and the voltage is applied just across. So if you look at that, if you have current here, the armature current, that will split into two. One is IL going to the load, and the other one going to the field. And remember that the RF usually much higher, like is showing the example, like 200 ohm, and the armature resistance is like 0.1, 0.2. It's like 1,000 times that. So that's why the field current will be always much smaller than the armature current, much smaller than the terminal current. But the question is, you're supposed to generate voltage, and we're going to talk about it in this lecture, that yes, you want to apply the voltage to the field, but first, the field, that's like, I mean, which one comes first, you know, the egg or the chicken? That's the voltage VT comes from EA, right? And EA, the induced EMF comes from what? Flux. The armature voltage E, it comes from what? It's equal Ka phi omega m. Okay, you have the external torque. It will rotate the speed, give the speed. You have the constant, but phi, this is what phi? That's the flux, that's the field. But the field is going to get it from outside. Outside is not getting it. So how they will work? I'm going to explain this problem, how it will be solved. Another connection, you might find that that's the EMF. You have the resistance, that's the armature, and you might connect the field in series. So they call this series excited DC machine. So that's series excited DC machine, generator or motor. You can have, you can split the fields into two groups, one connected in series and one connected in parallel, and they call it compound connection, compound DC machine. Like you say, okay, that will have part is connected in series, and part is connected in parallel. So we call this compound. And every connection has its own advantages and application. And we can write the equation for it. Anyway, and also compound can be split into two types, short compound, long compound, but I don't want to go in more details connection. That's enough for the basic connection of the DC machine. And simply it depends on how you connect the field or how the field winding is connected with the armature. When you go to the lab, you're going to find the magnetization curve of the DC machine. What does it mean, magnetization curve? The magnetization curve, you have the machine, that's the DC machine. Let's say talk about generator. You got the stator, that's outside. And has four poles machine here, and you got the rotor inside, and of course the all winding of the stator connected to supply the voltage. So what you are going to do, you want to see the effect of the field current on the magnitude of the voltage produced in the air gap, or we'll call it the armature voltage. Simply, we said that EA is the induced EMF or motional EMF, or the voltage produced across the brushes in the DC machine. And we said that in the equation that it's equal Ka phi omega m. We will need to find the magnetization curve, or the open circuit test for the DC machine when the speed is constant. Because of course, if you change the speed, the voltage will change. So I don't want to take another factor with me when I do the experiment. So I will fix this one. Will be constant. The speed. Ka depends on the dimension of the machine. I'm not going to change any dimension. The same number of turns and everything, the size of the machine, not change. So that one also is constant. So what I have left? Phi, the flux. So what is the flux? It's the magnetic field inside the machine under each pole. So I want to see the effect of the flux on the EMF, how it changes, how the induced EMF changes with the flux. But it's hard to measure the flux. So I go back and say, okay, what produced the flux? So what produces the flux? Magnetic field. The current in the field, right? So you have the field here that produce the magnetic field. That's as we said, that RF winding, and I have the voltage here. So what I'm going to do, I'm going to have power supply, variable power supply. And I start to change the current by changing the voltage, or I have another way to do that, and that's also a good idea. I have the field, and I have external variable resistance. I just get the fixed voltage, VF, fixed, 100 to 150, depends on the rating of the machine. And then I start to change the resistance. Even sometimes we put like switch here, so I can even make it first equal 0 in a way. So I start to control the variable resistance to change the field current. And when you change the field current, you are changing the flux. And I start to measure the voltage. But the problem is EA is inside the machine, not the B terminal. So how I do it? Very simple. If I sketch for you the separately excited equivalent circuit, that's the armature voltage produced across the armature, and that's the equivalent resistor. That's the resistor. And that's the voltage. That's the V term. And supposedly that's the armature current. And you have the field circuit on the other side. And you already have your voltage source constant, but you are changing the resistance to change the current. And even you are going to add switch here. So when you start, the switch was open, so the current will be 0 before you start. And you put the resistance, the rheostat, like the full resistance. So when you turn on the switch, or you close the switch, then the resistance is really high and the current is so small. So you start with a very small current. And how can I measure EA? You just put the voltmeter here across the terminal. But you will say, but this voltage is going to measure the terminal voltage, not the EA. Well, all what you're supposed to do, no load. You don't put no. So what happens if you don't have load? IA will be equal to 0. So in this case, we know that V terminal is equal EA minus RA IA. So if IA is equal 0, so the terminal voltage is equal EA. So I'm measuring EA, whatever produced across the brushes. So that's how you are going to measure EF. And you are going to put a meter here so you can measure the M, IF. So that will measure IF, and that will measure actually now EA. Here you go, you are set. You start, and then you sketch the curve. So what you will get curve to any magnetization curve will be like something like that. Every time you're increasing the field current, the EE, the inducing EF is increasing till it reaches saturation. And you can divide it into like 3 regions. The first region is linear, and then start to get non-linear, and then reach saturation that whatever, when you increase the field current, it's fixed. So 3 regions: linear region, then non-linear region, and then the saturation. They like to operate DC machine near saturation region, and we'll mention why now. So that's the way that's open circuit test actually. So you can get what you call this curve, magnetization curve. Is it important? Of course, because if you want to produce certain voltage or specific value of voltage, so you got to know what is the field current, the value. So how you know the field current? Like in the example that we did here. this numerical example, but everything was given. That's, I mean, but actually, in the practical life, we don't know. You know the load, you need 200 voltage, you need the load need 20 amp, and then you calculate, then you get EA. So you find, okay, I need 202 voltage. Then what's the appropriate field current? This is the life. I mean, no practical. Oh, this load 20 amp, it needs what the amp here, if you calculate, you see 250 divided by 200, right? So what you get, 0.125 amp. How you get this done? You got to know that the right value for the EA. So for this load, you need 202 voltage EA, armature voltage. So you go to the characteristic given for each machine between IF and EA. Is it good? Yes, for every machine there's a curve like that. Then I said, okay, I need 202 for my load. To supply the load by 200 volt, I need 202 voltage armature volt. So I go there, and then I go down there. Then I find that it's equal 1.25. I need 0.125 amp. In the data sheet of the DC generator, we have the resistance of the field. And then you're going to add an external resistance, and you adjust it in a way to get 0.125 amp. So that's how you do it. So it's important to know the magnetization curve of each machine. Of course, yes. So why? So it will tell us how much current we need in the field to supply specific value of the voltage.
What was the name of that?
This value?
Yes, what is that called?
The current of IF.
Oh, okay.
Yeah. And 202 voltage, that's the armature voltage for the induced EMF. So that's how we calculate the field current. So this open circuit test, and it will produce or gives the magnetization curve. Okay. It's done. We start connecting the external terminals by a load, and the terminal also be VT. The question is, EA is still the same, or will not be still the same? Again, question again. We did the calculation at no load, and then we found in our example that 202 voltage, that's the armature, required for the load 200 volt, 20 amp, and then from the curve we found that the field current 0.125. So I adjust everything 0.125. Then I start to connect the load, V terminal. This careful calculation. Are we going to get our voltage 202 across the brushes, and we're going to get 200 volts across the load as we planned for? Yes or no? You're going to answer. Just give any answer. No. Why? Okay, that's one. That's one reason. Because I did everything when IA was equal 0, right? Now we're going to have some calculation here. Depends on IA. When I did IA, I did in my account, I have 20 amp. So I need 202 voltage. So I got the effect. That's true. 202 will not be 202 in the terminal. That's right. I agree with you. But I was planning for the drop, right? So that's not. It's not going to be the same. Simple, in simple way. I will also use the same simple example to pole machine. And the beginning, no, and the armature can be represented like we have, let's say you have three turns. No, I'm not putting plus or dot, no current. So what's happening here? Well, if this is the north and this is the south, so you'll find that the magnetic field going from the north to the south. Okay. Now I'm going to apply the load. I will connect the load. So when I connect the load, what's happened? Armature current will go through that. So when you do have armature current, let's say you have positive, 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 and here coming out. That's the plus means in and dot coming out. What happens when the current go in the wine, in the coil or the wine? What happens? Actually, each turn has two conductors, and each conductor has current. So what will happen? Directly like this. No. Field, yeah, yeah. So magnetic field will be produced. So you got to imagine how the wire is perpendicular to the plane here. So if I sketched like that, when I make this is in and this is out, so I look here at that's make it plus and make it dot. So what happened? The current going in this conductor, you will have like many circles along in this direction, right? In this direction. And this one coming here, so you'll have magnetic field, but in different direction, right? So let's now make it nice here in this graph. You have magnetic in this direction. That's the main one. Let's just make it the same color, red. That's the main field current. We have the main field current in this direction. Just give an arrow like that. I'm going to show you one turn only. And this turn, we said that, let's say that that's in and that's out. So how the magnetic field around this one coming in will be in going in this direction, right? Anti-clockwise direction. So there will be magnetic field in this direction, right? And the other one coming out, it will be in the different direction. If you make, what is this blue circle? That's the magnetic field. And there are many of them, but just I'm taking only one for simplicity. And will be going in this direction. But in the air gap close to the poles, I don't care about in the middle. I care about the on the outside, on this side and this side, because I always concerned about the air gap. That's what the effect. So what's happening here is going to be effect of this flux produced by the armature on the main magnetic field produced by the field. Well, I'm saying, what is the effect if you have some object and this object like that, and you have force in this direction, and you have right. So what happens when you have two magnetic field? Flux produced by the armature is going to affect the main magnetic field produced. At this one to the right, what do you observe? What's the relationship between the magnetic field around the armature and the main field? Assisting, right? They are in the same. So what's happening here? The magnetic and what happened when you have this one and this one in this part decreasing, right? So you got one part increasing the flux, and you got in the bottom here decreasing the flux. Okay. So that one, you have something like that and you have something like that, it will be in this direction. So it will be like shifted. So you can say that there's distortion here in this side. So you got two effects. There is one effect, the magnitude increasing or decreasing, and there is one distorting the magnetic field, shifting the magnetic field from its normal position. If the flux is decreasing, so the EMF will decrease. The EMF will decrease. And if the flux is increasing, especially in this one, and we are operating close to the, as I said, close to the saturation region, so the effect will be demagnetizing, like decreasing the field because you operate in the magnetization. So the increase will be very slight. You're not having control. But the other one that's linear, obviously it can increase. But when you go saturation, no more increasing. So you will find that the magnitude of the voltage you are planning is not the same, is less. We call Armature reaction. And by the way, I didn't explain one to the left. It will be the same. Look at that. This one in the same direction. No, it's this direction, this opposite, and this one the same. The same thing happening at both. It happened at every single pole in the machine. So the two main effects that will happen by armature reaction, we call it armature reaction. What does it mean, armature reaction? When the armature current flows in the armature winding, producing flux, which affect the main magnetic field in two main effects, demagnetization and distortion. And in the end, you'll find that there are these two effects. What will happen? What will happen that the voltage you are planning for, you'll not get it. You'll get less than. And another thing, because there is a distortion, so it will happen a spark between the brush and the commutator. Because of the distortion, it will make not the voltage exactly zero at the time zero or volt. No, it's shifted, not as you plan. So it will happen jump from one value to value when the rotor rotating, and of course sparks. So that are the two effects. Of course, there is no problem without solution. So there are solutions to do that. Number one, they make something called interpoles. That's one. And another, let me get you the, I hope that I have a picture for it. That's what I explained to you, that when you have you see the magnetic field will be bended, that's the distortion, and this acts as you are expecting that the EMF will be 0 at the brushes. No, it's shifted. So actually, it will be the 0 along the other axis. That's what's called spark. Have the picture for the how to, but what happened that if you remember that's one ball. If you have the winding, the main winding, they put winding here in the pole shoe to why they put another winding? So the current will go in different direction to balance the effect of the demagnetization. And for big machine, DC machine, you have, for example, here one pole, and you have maybe another one. You have 4-pole machine. So what do? They put small poles between them. They call it interpoles. So it's either you add this winding with the poles, or you have interpoles between them. But it's kind of expensive. They don't do it with the small machine, but they make it with the big machine only. That's the magnetization curve, and that's the normal one. So the armature reaction, and you say, okay, this is the voltage that I want, 202 voltage. And then you go to the current. And then you'll find that this current 0.125 amp. Then it's not. It's not. So what is the real voltage you will get? If you added the armature reaction effect, this one will not be, this is the real current that you calculate. You'll find actually the armature reaction, you can represent it by delta, all right, delta IF. And the real one, it will be here, if you maybe it will be like 1.1 amp only. So maybe the effect of the armature reaction is equal to 0.025 amp. So that will be the real, and that's the actual voltage you're going to get. Maybe it will be 190 volts. So to count for it, you got to calculate the armature reaction effect for the DC machine, so you can know the real one. That will show you the real voltage you're going to get, not the 202. No, you're going to get 190 volts. That's how you can know what's the voltage. But in application, yeah, that's the effect, how I can know the effect. But if I want to get the 202 volts, what should I do? I should actually add this effect, and I see what the new field current that will give me the 200. It will give me more, that's true. But I see what is the effect. What is the effect? Is reducing by 25% of the armature current or not? And then I add it, and I get the new field current that's reasonable, or I mean, enough to give me the 202 volts. All right. So, of course, you cannot have many curves, because this curve at constant speed and IA equals 0. So you cannot sketch magnetization curve for different armature current. No, there is nothing called magnetization curve for IA equal 10 ampere or 20 amp. It's only for IA 0. So the only way to calculate, find the armature reaction effect added to the current, it will give you higher field current to get the 202 volt. And I'll show you next time example how we do that by practical example.